There are a number of types of intermolecular forces, and the kinds that occur between neutral atoms and molecules are called van der Waals forces. Within the van der Waals forces, there are several different types of interactions that can happen, and one of them occurs between literally any kind of atom or molecule. These are the dispersion forces. The way these work is that any atom or molecule can develop something called an instantaneous dipole, or momentary dipole. This occurs when the electron cloud surrounding the atom or molecule can arbitrarily shift to one side, producing an uneven distribution of electron density. Because of the asymmetry, one side will be very slightly partially negative, and the other will be very slightly partially positive, resulting in a tiny dipole. This instantaneous dipole can generate an induced dipole in another molecule, as the slight partial negativity can repel the electron density on the other molecule. The electrostatic attraction that occurs between the instantaneous dipole and the induced dipole is the dispersion force. Dispersion forces are very weak, the weakest of all intermolecular forces, because the instantaneous dipoles are so tiny and fleeting, but they can become significant for larger atoms and molecules which have larger electron clouds. We can observe this phenomenon by looking at the melting and boiling points for the diatomic halogens. As the atoms get larger, the dispersion forces between them become more significant, which is why fluorine and chlorine are gases at room temperature, bromine is a liquid, and iodine is a solid. The larger the atom, the further away the valence electrons are from the nucleus, and the more readily they can form instantaneous and induced dipoles. The measure of how readily an atom can distort its electron cloud is called polarizability. The more it can distort, the more polarizable it is, and thus the more strongly it can participate in dispersion interactions. The shapes of molecules also affect their ability to participate in dispersion forces, as a greater surface area will allow for more interaction. We can look at various hydrocarbons to see this in action. Look at neopentane, isopentane, and straight-chain pentane, which are all C5H12. Since these all have the same formula, it might be surprising that there is a discrepancy in the boiling points. But the more compact the molecule is, the less surface area that is available for interaction, and therefore it will boil more easily. The straight-chain pentane has the highest boiling point because it is participating in the strongest dispersion forces due to the larger surface area. And now we know what attracts non-polar molecules to one another.